Hello everyone, welcome back to another kinetic tutoring episode. Today we're taking a look at 1.5 electron configuration, so let's get straight into it. The valence electrons of both Na and Mg are located in the third energy level. Which atom, Na or Mg, experiences a greater attractive force between the nucleus and valence electrons? Justify your answer in terms of Coulomb's law. Alright, so taking a look here, we can say that alright, so let's draw this out. We have Na and Mg, they're both on the third energy level, meaning they both have three rings around the nucleus. So that this is Na with three rings and this is Mg with three rings. But however, one of them has a larger radius, and this is going to be because one of them has a stronger nuclear charge. And this is due to it having more protons in the nucleus. So, and that's going to be Mg because Mg has the atomic number 12 while Na has an atomic number of 11, meaning that Mg has 12 protons and Na has 11 protons. And the way you would write this is if you want to write the effective nuclear charge, it's going to be the positive charge, which is given by the amount of protons, which is for the Mg's case would be 12, and for Na's case it would be 11. And then you subtract the amount of base electrons, which is the amount of electrons it has minus the valence electrons, in which in both cases the number is 10. So the effective nuclear charge of Mg is going to be 2, while the effective nuclear charge of Na is going to be 1. And so therefore we know that since Mg has a greater charge, that means that the electrons are going to be more pulled towards the center. And since the electrons make up the rings, if they are closer towards the center, that means that the ring or the electron cloud is going to be closer, and therefore the electron radius is going to be smaller. Alright, so let's move on to our next question. This one has the same thing, except we're comparing Na and K this time. And K has 4 rings. So Na is going to have 3 rings, and K is going to have 1, 2, 3, 4. And although K has more protons, in this case the amount of rings is going to outpower the amount of protons, because although the protons bring it more close together, that doesn't matter quite as much as the rings. Because if we take a look at Coulomb's law, Q1, which is the positive charge, Q2 negative charge, over R squared, we see that these are linearly proportional, meaning that as the positive charge increases, the force is going to increase linearly. Same thing with the negative charge. But as the radius increases, the force is going to decrease exponentially because of the square right here. So that's what makes the radius more significant than the amount of protons. Alright, so now let's move on to our third and final problem. Here it wants us to write out the ground state electron configuration. So what we have to remember is that we have the S, P, D, and F orbitals. S comes first, and then P, and then D, and then F. So from here, nothing too difficult. The first two are going to be 1s2, 1, 2, 1s2. And then these two are also going to be in the s orbital, so it's going to be 2s2. And then we continue. We approach our second orbital, which is the p orbital, and we have 1, 2, 3, 4, 5, 6. So there we're going to have 2p6. And then back to the s, this is going to be 3s, so we have 3s2. and then back to the P's, 3p6. And then finally we reach 4s2, which is when we get to calcium, 4s2. And from here, this is the base state for calcium, but it wants us to find the ground state electron configuration for Ca2+. So therefore, we're going to need to remove 2 electrons. And so we're going to remove the valence electrons, and those are going to be the ones on the outermost shell. And that's going to be the 4th shell in this case. I don't know why I wrote the 6 so small. It should be like here. And on the 4th shell, there's just these 2 s electrons, the 2 electrons in the 4s orbital. So once we remove these 2, you'll get the configuration of 1s2, 2s2, 2p6, 3s2, 3p6. There we go. Now let's move on to the next one, Fe2+. All right, so we do the same thing. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and then we get to iron, which is going to be 4s2, which is going to be the 6th one in the d orbital. But here, even though it's on the 4th row, this row is called the 3d. So we have the 3d6 right here. That's how you get the base state of iron. But however, we're going to need to remove 2 electrons once again. Sorry, I dropped my pencil. And once again, it's going to have to be the valence electrons, which is going to be in the s orbital on the 4th layer right here. So once we get rid of these 2, you get 1s2, 2s2, 2p6, 3s2, 3p6, 3d6. Now, if we look down here at Fe3+, we see that it's the same thing, but you remove 1 more. And in this case, you're going to want to remove them. Sorry, dang, I just got rid of it, but I think I remember. Yeah, it's going to be 1s2, 2s2, 2p6, 3s2, 3p6, 3d6. So, I have the rule pulled up right here. Or no, I don't, but the rule is, oh, I don't know why that popped up. But the rule is when you have these, what you're going to want to do is you're going to want to remove from the P first. So, from the p orbital first, and then the s, and then the d. So if we remove 1 from the p orbital, you get 1s2, 2s2, 2p6, 3s2, 3p6, 3p5 because we removed 1, and then 3d6. So there you have it. All that happened is we just removed 1 electron from the 3p orbital because that's the one that comes out first. And now let's take a look at O2-. Alright, so let's first write the electron configuration for just oxygen. That's just going to be 1s2, 2s2, 2p4. That's going to be oxygen, but it's O2-, so we want to add 2 electrons. And of course that we're going to continue adding them in the 2p orbital so we can fill out that orbital because in its ground state it needs to be filled out before we can go to the next one. So add 2 electrons, you're going to get 1s2, 2s2, 2p6. And there you have it. That's how you go about solving those 3 problems. And with that, you should be able to solve and figure out everything in 1.5. I hope you learned something, and if you did, or if you enjoyed the video, make sure to leave a like and subscribe. That helps out the channel a lot, and I'll see you guys next time.